Okay, welcome again. In the previous class, we have discussed the properties of complex exponentials and sinusoidal signals in continuous and discrete domain. So what we have concluded there is that if we have a complex exponential signal in continuous domain or a sinusoidal signal in the continuous domain, and on the second hand we have a complex exponential or sinusoid in the discrete domain. So there were some differences between them. The first difference was this is periodic always with a time period of 2 pi by omega. These two signals, they may or may not be periodic depending upon whether the frequency omega by 2 pi is a ratio of two integers. Okay, if it is a ratio of two integers, then only it is periodic, otherwise it is aperiodic. The second was these signals have infinite bandwidth, whereas the frequency of these signals, discrete time sinusoids or complex exponentials, is limited between pi and minus pi. Or you can say in terms of f, it is limited between minus 1 by 2 to 1 by 2 only. Okay, and the third difference was that in continuous time, as you increase the frequency, your oscillations, the rate of oscillations, it starts increasing. With this is not the case here. So as you increase the frequency from 0 DC frequency towards pi, the frequency of the signal starts increasing, but when you reach at pi, you get the highest frequency. Okay, and beyond that, the frequency of the signal again starts decreasing, and when we reach at 2 pi, it becomes similar to the frequency 0. Okay, so low frequency signals are near 0 and 2 pi. High frequency signals are close to pi or minus pi. This is what we have concluded in the previous class. Now today we will discuss the significance of these signals. Why we study complex exponentials and sinusoids? What is the importance of this? Okay. So the important thing is that these signals, they act as the building blocks, both complex exponential and sinusoids, whether it is continuous domain or it is a discrete domain, they are the building blocks for other signals. And how they act as building blocks, that we will discuss here. Suppose we have a continuous time complex exponential xt in the form of e raised to power j omega naught t. Okay, with the angular frequency of omega naught radians per second. Let us suppose we generate a set of harmonic signals. Okay, we define a class of harmonic signals, suppose skt, which is equal to e raised to power j omega naught kt, where k is maybe 1, 2, 3, and so on. Okay, or you can also take 0, maybe start from 0, and you can also take negative values. What you mean by harmonic signals is that if you have a set of harmonic signals, all these signals have a frequency that is the multiple of a single frequency. Okay, it means if you define, this is a set of signals. I have used the subscript here k. Okay, so k can take any value. If k is 0, it is e raised to power 0, 1, it is a constant signal, of course. If you define as 1t for k is equal to 1, you will get e raised to power j omega naught t. For k is equal to 2, you get another signal as 2t, which is e raised to power j 2 omega naught t. Similarly, for 3, you get S3t, which is e raised to power j 3 omega naught t, and so on. So what is the property of these signals? This signal S1t has a frequency omega naught. This signal S2t has a frequency 2 omega naught. Then S3t has a frequency 3 omega naught. Okay, it means all these signals, they have a frequency which is the multiple of a single frequency, and that is omega naught. So one signal has a frequency omega naught, other frequency will be 2 omega naught, then 3 omega naught, 4 omega naught. In between there is no frequency. Okay, so these signals are called as harmonic signals. Okay, and these signals will have different time periods. If for S1t, the time period is suppose t, which is 2 pi by omega naught. For this signal, the time period suppose t2, it is 2 pi by 2 omega naught. For S3t, your time period t3 will be 2 pi by 3 omega naught. Okay, so in general, for this signal skt, your time period tk will be 2 pi by k times omega naught. Okay, and if 2 pi by omega naught is t, if this value is equal to t, I can write t2 as t by 2, I can write it as t by 3, or in general I can write it as t by k. Okay, so the first signal has a fundamental frequency omega naught, its time period is 2 pi by omega naught. The second signal has a frequency which is double of this, and its time period will be half. Okay, similarly 3 omega naught frequency, t by 3 will be the time period. Now if you combine all these signals together, and if you add them together, so if you form a series of skt where k can vary from minus to plus infinity, what you will get? Okay, this is summation of all the harmonic signals starting from minus to plus infinity. So what do you see how this signal will look like? What will be the signal, final signal? This is going to be a periodic signal with a time period of t, that is 2 pi by omega naught. And how? See, this signal S1t has a time period t which is 2 pi by omega naught. Okay, so in this case the time period is half. If I multiply this with 2, I can again get t. If I multiply this with 3, it will be again t. If I multiply in general this with k, it will become again t. So what it means? That if this signal is periodic with t, this signal is periodic with a time period of t by 2. But if it is periodic with a t by 2 time period, it will be also periodic with a time period of t. Okay, let me elaborate this. Suppose we have a signal, and let us suppose that the time period of this signal is 1 second. Okay, this is the time period t, which is equal to suppose 1 second. Okay, it means it is the minimum time after which the signal starts repeating. If this signal has a time period of t, you can also say that this signal has a time period of 2 seconds. Means in place of taking one cycle, if I take 2 cycles at a time. Okay, if I take this as one cycle, one time period, so the same 2 cycles you will get ahead. Next 2 cycles will also be similar to this cycle. So whatever is this time period, the same is this time. It means if the signal repeats after 1 second, you can also say that it repeats after 2 seconds. It repeats after 3 seconds, and so on. Okay, so in general, if this time period of the signal is t, It means if it repeats with time period of t, it will also repeat with a time period of 2t. Okay, it will also repeat with a time period of 3t, right? So if this has a time period of t, or in general you can say that when you have different signals, how you find the common time period? It is nothing but their least common multiple. So the LCM of all these time periods is nothing but 2 pi by omega naught. Okay, so if this signal is repeating with a time period of t, it means this has a time period which is half of this. Okay, like this. Suppose this is 2 seconds, this will be 1 second. Okay, this is twice of this. Then this is t by 3, 1/3 of this. That is 1 by 3 second, and so on. So what you ultimately get, it means if you have a linear combination of complex harmonic signals, what we are going to get is a periodic signal at the output, and this signal will have a time period which is 2 pi by omega naught. Okay, so you can write this equation as so st, which is a linear combination of skt, okay, and this skt is nothing but e raised to power j omega naught kt. So a linear combination of complex exponential harmonic signals is always periodic, and the time period of this signal will be 2 pi by omega naught. Okay, now comes the reverse question, that if the signal is periodic in nature, okay, so can we express this signal in terms of a series like this? Okay, can we express a periodic signal in a series which is a series of complex harmonics? And the answer is yes. That is what we get the Fourier series. Okay, so in the Fourier series you go in the reverse direction, means the periodic signal is given to you and you have to decompose this signal in terms of harmonics, complex harmonics. Okay, so any signal which is periodic, it can be decomposed in the form of complex harmonic signals like this. Okay, and along with this we introduce a coefficient ck, which is called as Fourier series coefficient. Okay, this ck basically determines the magnitude of the various frequencies, okay, which are to be added together so that you get a periodic signal, right? And the problem in the Fourier series is just to find this ck from st. Okay, now st will be given to you, which is a periodic signal. You have to find its Fourier series coefficients, and we have an equation for that. You have studied in signal system also how you get that, this equation that we may discuss later. Xt e raised to power minus j omega naught kt dt. This is equation number 2. This is equation number 1. This is the Fourier series. This is called as the inverse Fourier series. Okay, so what you do, if xt, I can write it as, if a signal st is given to you and you have to represent it in the form of Fourier series, that is in the form of harmonic signals only, you have to compute these coefficients. So when you put k is equal to 0, you get c0, the first coefficient, which is nothing but 1 by t integration of st dt, because e raised to power 0 will become 1. So this is nothing but the DC value or the average value of the signal. Similarly, you find C1, you find C2, you find C minus 1, C minus 2, and so on. You get all the coefficients. Once you find all the coefficients for this signal, you put these coefficients in this series, you will get its Fourier series representation. So ST will be finally represented like this: C0 plus C1 e raised to power j omega naught t plus C2 e raised to power j 2 omega naught t plus so on. Similarly, C minus 1 e raised to power minus j omega naught t plus C minus 2 e raised to power minus j 2 omega naught c, and so on. So when you decompose the signal in terms of complex exponentials only, this series is called as the Fourier series. Okay. And how you get this omega naught from ST, that you can simply see what is the time period. So from that time period you can directly calculate, isn't it? Like suppose if I have a waveform like this, okay, a square wave. Suppose I take this is ST, okay. So this is the time period. This may be any value t. So once you get this t, you can find its fundamental frequency, that will be 2 pi by t. It means when you decompose this signal in terms of the Fourier series ck e raised to power j omega naught kt, this omega naught, which is the fundamental frequency, is nothing but 2 pi by t. So when you write its Fourier series, this signal will be decomposed now in terms of complex exponentials only, but only harmonic frequencies. Okay, so you have omega naught frequency, then 2 omega naught, then 3 omega naught, 4 omega naught, and so on, right? And why we introduce this coefficient ck here? The reason is that you may have two different signals in time, both may be periodic. Okay, let us suppose I take a signal like this. Maybe suppose this is the signal. Okay, this is a periodic signal, and this also has the same time period t. So when you write its Fourier series, the equation will be same, but how you differentiate them, that is basically controlled by this coefficient. So for this signal, although the fundamental frequency of both the signals is same, but their Fourier series coefficients are going to be different. Okay, so this is called as complex Fourier series. And anyhow, if you decompose e raised to power j omega naught, means what you can get also is a trigonometric series. In that you have c0 plus c1 e raised to power j omega naught t. Similarly, you will have c minus 1 e raised to power minus j omega naught t. So these two frequencies, in case c1 and c minus 1, they are same, you can take them as common, and inside this product this will become a cosine function. Okay, and if c minus 1 is the minus of c1, you will get minus sign here. In that case you will get a sine function. So finally you can say that this signal or this signal, it can be represented in terms of sine and cosines only. Okay, so that is why we have said that these signals are the building blocks, because any periodic signal can be generated from complex exponentials or sine and cosine functions. So sine and cosine functions are the complex exponentials, they become the building blocks. Okay, so whenever we talk about the frequency, so a single frequency means a pure cosine or sine wave, or a pure complex exponential signal. Although you can see that this is a periodic signal, it does not means it does not have frequency. It has its own frequency, that is 2 pi by t. Okay, but when you go for the frequency analysis, you have to decompose this signal in terms of sine and cosine functions or complex exponentials. Okay, so this signal itself can be generated from sine and cosine functions. Okay, this signal can also be generated from sine and cosine or complex exponential signals, right? And how basically that is done, I will just give one more example on this. Suppose you have a square wave, okay, maybe like this, and so on. This is a function st. When I decompose this function in terms of the Fourier series, I get only e raised to power j omega naught kt. Okay, it means you have to compose this function in terms of complex harmonics, and you can combine the positive and the negative similar frequencies. You can get sine and cosine functions. So ultimately this function is going to be represented in terms of sine and cosines. Okay, now when you generate this signal from its harmonics, it means if you add all these harmonics together, all the frequencies together, what you are going to get is this signal back. Okay, so suppose what we do, we have the first harmonic that will be having the same frequency, which is the fundamental frequency of this signal omega naught. Then the second will be 2 omega naught, then the second will be 3 omega naught. Okay, so this is the time period of this function t. So omega naught is 2 pi by t. So the first function that will get, it will be having a time period which is similar to this t. Okay, because the first frequency is same. So you may get this first function, suppose a cosine wave like this. Okay, the time period is going to be exactly same. Of course the first will be constant, that is a0, which is a DC component. Then a1, it is the Fourier series coefficient for the first harmonic. Then for the second harmonic a2, and so on. Okay, so then you have second harmonic which is having a frequency 2 omega naught, so double of this. Okay, then you are having a frequency 3 omega naught, 3 cycles in the same time period, and so on. And when you add all these signals together, you are going to get the square wave. Okay, and how that is done, when you have just first harmonic, maybe you are getting a wave like this. Suppose when you add the first two harmonics, a0 and a1, you will get a wave like this. If you add more harmonics, you are getting more and more smooth square wave. If you add 100 harmonics together, you will may get exactly a square wave like this. Okay, but there are some problems, like at the edges where there is a discontinuity, this series never converges to the original value. There are some, you can say, a rise, there is some peaks here, but in between where the signal is constant, you can get the flat portion exactly. Otherwise this is called as Gibbs phenomena, that we may discuss when we discuss Fourier series somehow again. But this is the basic concept why we study the complex exponential signals. Okay, because any periodic signal can be decomposed in terms of complex exponential signals, or alternately you can say in terms of the sinusoidal signals. Okay, so that is why they act as the building blocks. So whenever we start the theory of signal processing or signals and system, we always start from the cosine and sine functions, sinusoidal functions, or complex exponentials, because they play a major role in the signal processing theory. This is one thing. The second concept behind why we use complex exponentials, I will discuss one more concept important. When you pass a signal, suppose xt, through a system, okay, and let us assume this is the LTI system, that is a linear and time invariant system. So how we get the response of a LTI system? It is nothing but the convolution of xt with the impulse response of the system. So this system has an impulse response which we denote by ht, impulse response. Okay, impulse response means what is the output of this when the input is a impulse signal. If you apply delta t here, if xt is delta t, that is unit impulse, yt is nothing but ht. This is what is the impulse response. Okay, the response of the system basically due to impulse, that is called as impulse response. And once you know the impulse response of a LTA system, linear time invariant system, you can express the output of the system as the convolution between xt and ht. So this is the convolution, and you have studied in signals theory, convolution is an integral basically defined by x tau h of t minus tau d tau, and it is a commutative function or property. You can also write it as h of tau, x of t minus tau, and d tau. Okay, so when you find the convolution of two signals, you know there are four basic operations. We first fold one signal, then we shift it, then multiply it, and then integrate. That is how you get the convolution of the two signals. Okay, now you are applying, this is the basic concept how you find the response of ALTA system. We use convolution integral to find the response. Now if I apply a periodic input here, if this x is periodic input, you can compute the output of the system using the convolution integral, of course. But if you want to see that how this system responds to the various frequencies which are being passed through the system, you cannot get that information from the time domain, because in time you are unable to see the frequency information. So what we do is that if you suppose you have a periodic signal here xt, which is processed by a LTI system, and you have to find its output. This is a periodic sequence, periodic signal. Okay, so you can again take the help of complex exponentials. Okay, because if the signal is periodic, I can write xt in terms of its Fourier series. Okay, it means I have decomposed this signal in terms of a series like this: c naught c1 e raised to power j omega naught t plus c2 e raised to power j 2 omega naught t plus so on. So this signal is now a linear combination of different signals, and since the system itself is linear, so linear system means what? That the output due to a linear combination of different inputs is equal to the sum of their individual outputs. Okay, this is what is the linearity property. It means output of the system, I can calculate it as output, what is the output due to this, plus what is the output due to this, plus what is the output due to this, and so on. All these individual outputs, if I combine them together, you can get here the output yt of the system. Now since in the input signals we have only complex exponentials, so we have to first see what is the response of a LTA system to a complex exponential. Okay, so for that I take input as, if the input signal is only e raised to power j omega naught t, a complex exponential, what will be the output of the system? This is convolution. I assume that it has some impulse response ht. Okay, so yt is nothing but integration of h of tau t minus tau d tau, And what is xt in this case? Xt is e raised to power j omega naught t. So you can write this equation as integral of h of tau xt minus tau. So xt is e raised to power j omega naught t. You can write it as e raised to power j omega naught t minus tau d tau. And this will become finally, this equation will become integration of h tau e raised to power, it will become j omega naught t multiplied with e raised to power minus j omega naught tau and d tau. So this I can write here as yt will be, now since the integration is with respect to tau, this becomes a constant factor. You can take it outside the integration. You can write it as e raised to power j omega naught t multiplied with this integral h of tau e raised to power minus j omega naught tau d tau. Okay. And if you see to this integral, if you remember from signal system theory, this is nothing but the Fourier transform of ht at a frequency of omega naught. Okay. When you define the continuous time Fourier transform CTFT, how you define it? It is defined as h omega is equal to integral of ht e raised to power minus j omega t dt. This is the Fourier transform of ht. And if you look at this equation, this is same. The only difference in the variables, in place of t we have tau, and in place of omega we have omega naught. Okay, so you have particular frequency here. It means this is nothing but h of omega naught. So I can write here yt as e raised to power j omega naught t multiplied with h of omega naught. That is the Fourier transform at omega naught frequency. This Fourier transform of impulse response is also called as the frequency response. So this is the frequency response at a frequency omega is equal to omega naught. So now you get a very important conclusion here, that if we have a linear time invariant system and if you're passing a purely complex exponential signal through it, what to get at the output? The output is the same signal, e raised to power j omega naught t multiplied with a factor h of omega naught, and h of omega naught is nothing but the frequency response of this system at that frequency that you are passing. Okay, so what it means, that you have a input e raised to power j omega naught t, you're passing it through a linear time invariant system. What you get the output is e raised to power j omega naught t, the same signal multiplied with h of omega naught. So h of omega naught is nothing but the frequency response of the system. This is the impulse response ht, and as a result you will get its frequency response nothing but its Fourier transform, that is ht e raised to power minus j omega t dt. Okay, so every LTI system has a frequency response. Okay, so in fact it is a complex quantity. You can have a magnitude and phase response both, but if you just concentrate on the magnitude response mod of h omega, so it may have some response. Maybe suppose it has a response like this. Suppose you have some system which has a frequency response like this. At a frequency omega is equal to maybe omega c, there is a null point or a dip, otherwise its magnitude, or we say gain, is unity. Okay, now if you pass any signal through this system, how I am getting the output? It is the same signal but it will be multiplied with a frequency response at that particular frequency. It means if I pass this frequency is more omega 1. Okay, if I pass a frequency omega 1 through this system, what is the output? The output is same. There is no effect because it is multiplied with 1. If I pass a frequency omega c, now at omega c your h of omega naught is 0. So this frequency is going to be stopped by the system. So this is how the system acts as a filter. Okay, so filter means you are passing some specific frequency bands and you are stopping some specific frequency bands. In this case, it stops only one frequency, that is omega c. It becomes a notch filter, right? Otherwise, if you have a frequency response like this, maybe 0 to omega c, your magnitude response is 1. And if you pass any frequency through this, from 0 to omega c, its magnitude is 1, so all the frequencies are passed as it is without any attenuation. So beyond omega c, which is maybe the cutoff frequency, the gain drops to 0. So any frequency beyond this omega c is stopped. So this becomes a low pass filter. Only the low frequencies from 0 DC signal to omega c are passed. Rest of the frequencies are stopped. Okay. Similarly, you may have a frequency response like this. So this becomes a high pass filter, because now at low frequencies your gain is 0, at high frequencies the gain is 1, so they pass through the system. So likewise you can have a band pass filter. Between omega 1 to omega 2 these frequencies are passed, so rest of the frequencies are stopped, or you can have a band stop filter. Okay, so the basic concept about filtering is that you have to control the frequency response. In fact, when you take any system, it has a frequency response, but if you can control the frequency response of the system by designing the system coefficients, you can get a particular type of response and that can become a filter. Otherwise, any system is a filter and any filter is a system, right? So this is another significance of complex exponentials. Okay, when you pass a complex exponential through LTI system, the output is the same signal multiplied with the frequency response. Now using this, you can have an idea that how the frequencies will be passed when they are passed through a system. Means now we have xt, which is a periodic signal which is processed by a LTI system, and yt. Now since this signal is itself is periodic, I can decompose this signal in terms of Fourier series plus and minus and so on. So what will be the output? It will be simply constant plus. Now when c1 e raised to power j omega naught t is the input, what is the output? C1 is the constant. This will be C0 first plus C1. When e raised to power j omega naught t is the input, output is e raised to power j omega naught t multiplied with h of omega naught. When this is the input, you have c raised to power C2 e raised to power j 2 omega naught t multiplied with h of 2 omega naught and so on, using the linearity property. Okay, so this gives you an insight that how the frequencies are basically processed by the system. Okay, because in time when you find the convolution, you cannot see which frequency is passed or which frequency is stopped. So the frequency at which the frequency response will be 0, that will be stopped. The frequency at which the frequency response is unity, that will be passed. Okay, so anyway, if you have to design a system as a filter, you have to design its basically frequency response. Okay, so you have to simply make one at that frequency where you which you want to pass. You have to make the response to drop to 0 at the frequency which you want to stop. So you can design a filter like this. Okay, so this is another important significance of complex exponential signals. Using the complex exponential signals, you have an insight that how the system basically processes the different frequencies when you pass a signal through a system. Okay, so I think this is enough for this lecture. Next we will discuss the significance in discrete time exponentials. There is a difference between the complex exponentials and discrete time harmonic signals, and then we will further discussing upon the sampling process. Okay, thank you.